everyone. My name is Shunit Agmon, and I'm here to present our work on analyzing deviations from monotonic trends through database repair. This is joint work with Youngmann, Amir, Gilad, Ester, Livshits, Mutay, Brit, Youngmann, and Kimelfeld. So, when we think about education and career growth, it's natural to assume that as a person gains higher education, their salary should grow. But according to the Stakeholder Growth Survey of 2022, this isn't always the case. If we look at the median salaries in the US, we see that it doesn't show a perfect trend over education level. There are some deviations. So we can ask, how far is this data set from actually exhibiting a perfect increasing trend? And also, what is the correct direction of the trend? Is it possible that as a person gains a higher level of education, they become overqualified and their salary should actually decrease? So, we tested it. And we found that if we remove less than 1% of the data, this is enough for a perfect increasing trend. But to get a decreasing trend, a more serious intervention is required. So I think we can safely breathe. So to formalize this problem, we defined an aggregate order dependency composed of a group by attribute, like education level, an aggregation function, like median, and an aggregate attribute, like salary. And we're searching for a cardinality repair, which is a maximum size subset of the relation that satisfies the trend. And the goal through this is to quantify and analyze the deviation from the trend. Now, this approach is actually a part of the well-studied problem of database repairs. We're given a database and a constraint. We want to find the minimal intervention, the minimal change that will satisfy the constraint. And this approach is actually complementary to traditional trend analysis approaches, where you fit a statistical model to the data and you measure the error or the goodness of fit. So instead of that, we're measuring the size of the intervention required. So let's look at another simple example. We have a relation here, and the trend is not satisfied because the average of the second group is too large. So we could repair it by removing two tuples and increasing the average in the third group, or we could remove just a single tuple and decrease the average of the second group. So there can be many different subsets that satisfy the trend, and the question is, how do we find the optimal one? Because naively going over all the subsets would take exponential time. So can we do better? And the answer is yes, using a dynamic programming algorithm. So the first thing we do is to compute all possible aggregation values that we can get from each group by using a subset of it. And then we populate a dynamic programming table where hi of x, where we consider only the prefix of the first I groups. We want the trend to hold for that prefix, and for the last aggregation value to be exactly x. And what this algorithm does is actually to reduce the problem from global, searching a subset to satisfy the entire trend from the entire database, to local, searching a subset of specific groups to satisfy a specific aggregation value. And this yields the following result. For some aggregation functions, a repair can be found in polynomial time, which is actually nice. So for this group of aggregations, what happens is the possible aggregation values, the number of them is actually bounded. For example, for max, the aggregation values can only be one of the original unique values. But for sum and average, this isn't the case, because every different subset can yield a different aggregation value. So the problem becomes only pseudo-polynomial. Which means that if we get the input in unary form, then it is polynomial. And we show that using different techniques in our paper. So to accelerate the search of the dynamic programming algorithm, we can use different optimizations. We first can calculate all of the possible aggregation values at once at the beginning of the search, which also opens the door to more optimizations custom for each aggregation function. And we can also prune the search. So suppose we know of some non-optimal repair that removes h tuples. then as we're searching for the optimal solution, we can avoid saving partial solutions if they already remove more than H tuples, since there is no way this is going to lead to the optimal solution. And how do we get such a bound? Using a heuristic algorithm which we developed. So in this algorithm, the idea is to iteratively remove the tuple that affects the most on the sum of violations. So for example, for this trend, with the maximum aggregation, we want an increasing trend, and some of the tuples are going to have 0 impact, the others, and if we remove, for example, tuple 1, 4, then it's going to reduce the sum of violations by 1. Removing this one would increase the violation, and removing this one would do nothing. So the algorithm continues iteratively until there are no more violations. So we ran experiments over 5 real-world datasets of different scales, where for each dataset we chose a trend expectation according to the most interesting attributes of the dataset. And what we see here is a comparison of runtime on the horizontal axis versus the number of tuples removed, the quality on the y-axis. So lower is better for both axes. And if we zoom in on this example of a real estate dataset, we see that the heuristic algorithm, represented by a triangle, ran in 40 minutes, which was faster than the 16 hours of the dynamic programming algorithm, but it was wasteful. It removed 1.37 more tuples than necessary. And this is also the case for different scenarios. Usually, the heuristic is faster, sometimes by an order of magnitude, but it may remove unnecessary tuples. So let's zoom in further on this real estate example, where we expect median house prices to increase with the year they were built. So newer houses should cost more. And this is almost the case, except for a violation in 2005 to 2009. Which trend direction is closer? Well, to get an increasing trend, we would have to remove 2.6% of the data, and to get a decreasing trend, we would have to remove over 20%. So definitely closer to increasing. And if we look at the tuples we removed there, we see more condos and single-family homes, and more centered in Los Angeles, which suggests that it has to do with the housing bubble, which ended in those years. So the removed tuples can help us measure and explain the deviation from the trend. And finally, we compared two well-used outlier removal methods. Outlier removal does not guarantee to satisfy the trend, so after we did that, we also ran our repair algorithm, and this is the number of tuples removed for each of these scenarios. And when we compare that to the number of tuples removed only by repairing without outlier removal, we see that removing outliers actually harm the performance. So it caused us to remove way more tuples than necessary, which suggests that the tuples that are statistical outliers are not necessarily the ones causing the deviation from the trend. We also implemented a demo, which allows us to go into and find explanations for the removed tuples, and we're showing it also tomorrow at 3:30, so you're welcome to check it out. And yeah, so let me just sum up. We formulated trend expectations as a database repair problem, and we used the repair to get some insights. Insight on the distance from satisfying a trend through the size of the repair, and also on the reasons why the trend doesn't hold through looking at the specific tuples removed. So yeah, thanks.
Thank you so much for the exciting talk. Questions? Alright, I can ask a couple of questions. So does the user have to provide these monotonic trends? What is the expectation of the trends?
Yes, so the user has to specify their expected trend, the grouping, the aggregated attribute, and the aggregation function, and if they're expecting an increase or a decrease.
So is there a single trend, or is there a combination of trends or more than one trend that they're working on?
So we are supporting a single trend at a time, but in the demo, it is very easy to switch and find out what happens if we...
Yeah. My second, if there are no questions,
yeah.
Actually, it's a similar question. So here we assume that the trend is monotonic. So, but how do you know from the user's knowledge that it's always monotonic, increasing, decreasing? What is like is a sine curve, for example?
Right. So that's a great question. So the question is about, can we support non-monotonic trends? And this is, the heuristic algorithm can support it easily because it's just a matter of defining the impact for this problem, or the measure of violation to redefine it. But the dynamic programming algorithm would not work for this case. But it is very interesting to consider different algorithms to solve this problem. There have been a bunch of papers about supporting an expectation that isn't necessarily monotonic, but not in this one.